Okay, so I'm going to try to go through 4 related rates problems, and it'll take a little bit of time to do those 4. If you would like a copy of this thing, I'll actually attach this into Google Classroom as just an optional extra piece. So look in Google Classroom to extra related rates problems, and you will see that there if it helps you to look along as you go. But I do think these will be helpful instead of just looking back through some problems you've already seen before. So anyway, we'll look through a couple of problems here. We'll do 4 of them in this video, and I have 4 more for another one. So this is one, I haven't done a problem like this with you guys, but what I have is some kind of a curve. And as it turns out, if you graphed this particular thing, x to the 4th plus 3x squared is some kind of a curve like this, okay? And I've got some particle that is moving along this curve, and it says specifically that dx dt is 5. So in other words, the particle is moving this way at 5 units per second. Now at first, down here, most of the motion is side to side, but if it wants to move 5 units to the right, over here, it's going to go up very, very steeply. So I would like to know what is the rate of change of y with respect to time at that moment when x is 2. So let's see what happens. Now, dy dt is equal to 4x cubed dx dt plus 6x dx dt. Now again, mathematically, this is pretty simple because I know that x is given to be 2 at a given snapshot of time. X isn't always 2, but at this particular moment in time, I want to know what is happening when it gets over to the number 2. dx dt was given to be 5. Again, x was given to be 2 and dx dt was given to be 5. Everything is just simple numbers, and we find that we get 220 if you were to multiply that out, and that would be 220 units per time, I guess seconds or something like that. So what's interesting about that, if that's the case, to go over just a little bit, you're going to have to go a whole lot because the graph is very steep over here. Now, second one, we have a spherical balloon, and it says gas is escaping at 10 cubic feet per hour. Okay, so we've got this sphere like this, and the gas is escaping. So I'm telling you that dv dt is negative 10 cubic feet per hour. And it says, how is that radius changing? Now, again, the first problems are going to be relatively simple, but we'll see what happens. We have a master equation when we talk about the volume of the sphere, which is 4/3 pi r cubed. So dv dt would be 4 pi r squared. We've done this one in class a couple of times, times dr dt, because remember, we're taking the derivative of this with respect to time, because time is really what's controlling our story. Now, in our story, it says dv dt is 400 cubic feet. Oh, wait, 10 cubic feet per hour. Just kidding. And it says, at what rate is the radius changing when the volume is 400? Oh, no. I need to go figure something out. This says the volume is 400, but they didn't bother to tell me what the radius is. So I need to go through and do a little bit of math on this. So if I multiplied both sides by 3/4, I could say that 300 equals pi r cubed. To get rid of that 4/3, I'm going to divide both sides by pi and take the cube root. So the moment in time that we're talking about is the moment when the radius is the cube root of 300 divided by pi. That is not a very nice number, but it's all right. We can still do that. So according to this, we want to plug in the number pi and the number r, which is the cube root of 300 over pi squared, times dr dt, and that's what we want to know. And so everything else is a given. Now, what I chose to do is I chose to be a little bit lazy. All of these things are numbers. So I decided that what I would do for my particular problem is just see what the calculator does. So let's take 300 divided by pi, right here. I'm supposed to take the cube root of that, so let's raise that to the 1/3 power. This problem squared that, multiplied it by 4 pi. So this whole value right here is 262.5, and I want to take -10, because that's what I have on this side, and divide it by that answer. And so I found that dr dt is approximately -0.038 feet per hour. Well, if you're in a hot air balloon going across the tundra, you hope that you're not losing your volume or your radius very carefully, because it might be a rough descent. Okay, number 3. Familiar question. We have the ladder leaning against the wall. It is falling. And a ladder that is 10 feet long. Now, that's really important, because one of the things we've talked about in our class is it's really, really helpful if you ever have any constants. And the number 10 is a constant, so I can put that in the very, very beginning of the problem. So I know that x squared plus y squared is an even 100. And I know then if I took the derivative, I'd get 2x dx dt. I get 2y dy dt, and of course, the derivative of my constant is going to be 0. Now, what some people will do, I'll see people do it, is they'll just call it ladder. And then down here, they'll call it ladder squared. And so they'd write 2L times dL dt. But the thing is how is the ladder changing? Well, the answer is it isn't. So all of these things end up disappearing because they become 0. They're derivatives of constants. So it's no big deal. So notice that I haven't done my snapshot, but when we get down here, if the bottom of the ladder slides away at a rate of 1 feet per second, that means x is actually growing at 1 foot per second, positively. It says when the bottom of the ladder is 6 feet from the wall, so you'll notice I gave you a nice little 6, 8, 10 triangle. So at that moment, I'm telling you x is 6. I'm telling you y is 8. I did not tell you what dy dt is, but I told you the answer was 0 because the ladder is not a collapsible ladder, it is constant. And so all we have left to do is go through a couple little pieces, and although the ladder is sliding at 1 foot per second away, if you do the math on this, you're going to bring the 12 to the other side. You're going to divide by 16 and reduce, you're going to get -3/4 of a foot per second. So it is sliding out faster than the ladder is falling for this particular story. Okay, now my last problem for this particular video. Water is flowing at 8 cubic feet per minute into this cylindrical tank with a radius of 4 feet. Well, the awesome thing is the majority of the time other than really crazy mathematical cylinders that are made up by math teachers to make students' lives difficult, this thing should be a constant 4 feet, because most cylinders over time, water flows in or flows out, but it moves up and down, but the radius is going to be completely unchanged. So when we talk about the volume of the cylinder as pi r squared h, I could plug in the number 4 very quickly because it's a constant and make it 16 pi h. And all of a sudden we have a very, very nice, easy story. And we could say then that dv dt equals 16 pi times dh dt, which is pretty nice. It's about as easy of a calculus question as you're ever going to see. Now, it says, how fast is the water level rising when it's 2 feet high? And what you're going to notice, the height doesn't even come into play. I can't even plug that in. But what I can plug in is it says right here that the water flows in the early stages. I should have written that down, at 8 cubic feet per minute. So if we put 8 feet cubed per minute here equals 16 pi dh dt, then dh dt is going to be 8 over 16 pi, which in other words, dh dt as a summary would be it is 1 over 2 pi feet every minute. And the kind of the cool thing is this was 16 pi times dh dt. It actually doesn't matter what height it was or anything about the radius. It is just always going to be that number of feet per minute because it's going to grow steadily as it works its way up the sides of the chamber. And that is as far as I wanted to go for this particular video. So that's 4 questions on this one. And I have 4 more on the next video, which is going to be probably a little tougher. Okay, so that's going to be what I'll call level 2. Okay, see you back in class.